All right, so we're in part 2 of 15.6. So we're going to do surface integrals on vector fields. So yesterday we talked about surface integrals on scalar fields. So we're multiplying the scalar function by the small element of area, summing that over our surface. Today we're going to integrate the normal component of a vector field over our surface. We need to know a couple of things before we do that. We need to define a few terms so that we can write our surface integrals. So the first thing we need to know is about oriented surfaces. So when we're talking about a surface and we want the normal component, we're interested in the normal vector. So the normal vector is going to play a big role. So an oriented surface has two sides. So a Mobius strip would not be an oriented surface because a Mobius strip only has one side. A Mobius strip, it's a strip with a half twist that's hooked together, and it just has one side. A Mobius strip only has one side. So an oriented surface has two sides, and oriented surfaces have two normal vectors. So if we have some surface here, like so, we have one normal vector that can go this way, and we have the normal vector that can go in the opposite direction. And I'll call that negative n. And the other term you'll hear for oriented surfaces is orientable surface. And we say formally we're not going to worry about it that much, but the formal definition of an oriented or an orientable surface is that we can define a unit normal vector at every point on the surface so our normal vector varies continuously over the surface. So we don't have any sharp corners, we don't have any strange things happening on our surface. So we can define a normal vector at any point on the surface. And when we talked about parametric surfaces the other day, if we have a parametric surface, R of u and v, our unit normal vector, our normal vector is given by the cross product of the partials of R, but our unit normal vector n is going to be the cross product, R sub u cross R sub v divided by the length, the magnitude of that cross product. And our second unit normal vector would just be in the opposite direction, just be negative n. So we have one that points up, one that points down, one that points one particular direction, one that points in the opposite direction. If our surface is given by an explicit formula for z equals g of xy, then what we do is, remembering back to what we learned about the gradient, if we have some function, some surface represented as g of xyz equals 0, then our gradient gives us a normal vector. So if we have our surface defined by z equals g of xy, we say that g of xyz equals z minus g of xy, and that equals 0. So I just subtract g of xy here, and this is my function that gives me my surface, and my normal vector n is del g over the length of del g. Because a gradient of a surface given by g of x, y, z equals 0 gives me a normal vector, and we divide by the magnitude of that normal vector to get the unit normal vector. And negative n is going to give me a normal vector in the opposite direction. So these are our unit normal vectors for our orientable surfaces. Everybody good with that? So this is one thing that we need to be able to do to write our surface integrals for vector fields, is come up with a unit normal vector. Now if we have g equals z minus g of xy, our gradient, I'm just going to write an equation for our gradient. Del g is minus dg dx I minus dg dy j plus k hat. This gives us the upward unit normal vector. Or this is giving me the upward normal vector. So when I have my surface defined in terms of g of x, y, z equals 0, del g gives me an upward normal vector. This is an upward normal vector. And minus del g is dg dx I, we just have the opposite signs, plus dg dy j minus k. And this is the downward normal vector. So for our upward normal vector, my k component is positive. For my downward normal vector, my k component is negative. And if we want a unit normal vector, we just divide our normal vector by the magnitude of del g. And this is important because your problems will state, and we'll talk about it in just a minute, but we'll be finding the flux upward through the surface. So they're talking about the upward unit normal vector. So is everybody good with how we find our normal vectors? And it's important to remember that if we have z equals some function of x and y, our surface is given to us by this, then we need to write our surface as capital G of x, y, z is z minus small g to find our normal vector, to use our gradient to find our normal vector. So we need to remember we want to express our surface, for what we're doing here, we want to express our surface as z equals some function of x and y, and then rearrange it into this form. Because it won't always be given to you in this form. All right, so now we need to talk about flux. We've talked about an oriented surface, orientable surface, and how we find our normal vectors. So now we want to talk about what we mean by flux. Flux is one of the big applications of surface integrals. It comes up in physical applications a lot. Electric fields, fluid dynamics. You talk about flux a lot. So let's talk about what we mean by flux, and then we'll be ready to write our surface integral on our vector field. So we have, here's our coordinate system. And we have some surface here. So there's our surface. And I'm going to draw a little element of area here. And I'm making it big In fact, I'm going to make it even bigger. I just want to be able to draw my... So we're going to call this little element of surface, this is delta S. So we're dividing our surface into these little pieces. And we're going to say that, and this is my surface S. We're going to say that we have a vector field, F, defined in our region here. And so at this in this particular small element of area, my vector field, we're going to say, is going this way. So that's F. And at this particular point, we also have our normal vector. And what we're going to do here, just to develop this idea of flux, is we're going to say that F is the velocity field of a liquid. So we have a liquid flowing through here, and our vector field gives us the velocity of the liquid at any point. And what we're interested in with flux, we're interested in the volume of that liquid that flows through this surface. So to find the volume of this surface, or of the liquid that flows through the surface, we want to, the component of F that flows parallel to the surface doesn't contribute anything that's to the liquid flowing out of the surface. So we're only interested in the normal component of F. And the volume that flows through this little piece of surface, delta S, is going to be given by the volume of the fluid that flows through in the direction of the normal vector. Well, that volume, if we think of this as the base of a little prism, the volume that's flowing through there is, this is the base, and the height is going to be given to us by F dot n. That's F dot n gives us the component that's flowing perpendicular to the surface. So if we take the dot product of F with n, that gives us the amount of liquid that's flowing through in the normal direction. So we're going to say that the volume of liquid flowing through delta S, and we're going to say per unit time, is F dot n times delta S. And we can think of F dot n as the height of this little prism above delta S. And F dot n is the component of F in the direction of n. And we're going to use the same argument that we've used a lot when we talk about these integrals. We're going to make delta S so small that we can consider F a constant at that point. So F isn't varying over this region delta S. Delta S is super tiny. So we're assuming that F is constant, and that this little element of area is a parallelogram. So the F dot n delta S, like I said, is the volume of a little prism sitting there above our surface. And we want to sum these quantities over the entire surface. So we're summing the normal component of F times the little element of area over the entire surface. And we take the limit as delta S approaches 0. And we get our surface integral. So does everyone understand, everyone clear what we're doing, what we're summing here? We're taking the normal component of F times this little element of area and we want to sum that over the entire surface. So we're summing the normal component of our vector field, the component that's normal to our surface, multiplying it by this little element of area, and summing that over the surface. So we can think of that as the volume of fluid. If we think of F given us a velocity field of a fluid, the volume of fluid flowing out of the surface per unit time. That's one way we can visualize what we're doing here. So we're going to sum this quantity over the surface, and we think of that as the volume of fluid flowing out of that surface per unit time. So we'll use that to define our flux integral, or our surface integral. So this gives us our flux integral. So our flux integral is the integral over our surface of F dot n ds. And the other way that we refer to this is the flux of F across S. So this is our surface integral of a vector field. The surface integral of a vector field is the sum of the normal component, is the integral of the normal component of F over our surface. So now we know what it is, we need to know how to evaluate it. So if z is given to us by g of x, y, then we said that we have g of x, y, z equals z minus small g. And our normal component, n, is del g over the magnitude of del g. Oops. And we also said that ds, when we have our function represented this way, is the square root of g sub x squared plus g sub y squared plus 1 dA. But this quantity, this radical, g sub x squared plus g sub y squared plus 1, this equals the magnitude of del g. So now we're going to substitute these quantities into our integral. So our surface integral of f dot n ds turns into a double integral over our region of f dot del g dA. And this is for our upward orientation. Our z component is going to be positive, so this is the upward flux through S, and R is the region in the xy plane. So this is how we evaluate our surface integral if we're given our surface in terms of z equals g of xy. F dot del g dA, where R is our region in the xy plane. Are we good with that? All right, if we have a parametric surface, if we don't have an explicit formula for our surface, if we have a parametric surface, if our surface is given to us by parametric equations, R of u and v, then our normal vector, unit normal vector, is our cross product of our first partials divided by the magnitude of that cross product. And ds with a parametric surface is our magnitude of our cross products times du dv, or dA, I'll say dA. And the magnitudes cancel again. And our surface integral, our flux integral, is of f dot n ds equals the integral over the region in the UV plane of f dot this cross product. And here R is the region in the UV plane. So these two equations give us our method of evaluating our surface integral of a vector field. Questions on the development? Okay. Let's look at a couple of examples. And I'm going to try to go quickly so that we can get through these so you have some examples to work from. So we want to find the surface integral of f dot n ds upward, where f is, our vector field is xi plus yj, and s is given to us by 2x plus 3y plus z equals 6 in the first octant. So first off, what is our surface? What is a surface? A plane. So we have a surface, we have a plane. And we're looking at the first octant portion. Here are our capital G, the function that we're going to find the gradient that's going to give us our unit normal vector. Let's say G is 2x plus 3y plus z minus 6. That's our implicit equation, implicit formula for our surface. So del G gives us our unit normal. So we're going to use del G to get our normal vector. Del G is 2i plus 3j plus k. So this is our upward normal vector. We need to, and remember in our formula, our magnitudes of del G canceled if we have our surface expressed this way, so we don't have to calculate the magnitude of del G. And f dot del G is what we're going to integrate. F dot del G is just 2x plus 3y. Now we need to figure out our region in the xy plane. We have our surface, we need our region in the xy plane. So I'm going to sketch this out really quickly. When we have a plane, we're just going to plot points on the axes. So we're up here at z equals 6 when x and y equals 0. We're out here at x equals 3 when y and z equals 0. And we're over here at y equals 2 when x and y are 0. So our region in the first octant is here. Our region in the xy plane is bounded by this line right here. So we use these points to find the equation of this line. This line is y equals minus 2/3 x plus 2. So that's going to be one bound in our xy plane. So x is going to vary from 0 to 3, and y is going to vary from 0 to minus 2/3 x plus 2. That gives us our region in the xy plane. So we end up with our double integral over our region in the xy plane is the integral from 0 to 3, x equals 0 to 3, y equals 0 to minus 2/3 x plus 2 of 2x plus 3y dy dx. This one's a nice, easy integral to evaluate. This comes out to 12. So if we think of F as a velocity field, and our flux integral gives us the volume, this would be the volume of the fluid flowing through this surface in the first octant per unit time. So it'd be flowing 12 whatever's per unit time, whatever our units are. Questions on that example? All right, this next one I just want to talk about the setup. I'm not going to go through the entire example, and then there's one other example I want to do. So if we had something like our field where we want to evaluate the flux integral, and F equals xi plus yj plus zk. So that's our field, and our surface is given by x squared plus y squared plus z squared equals 36 in the first octant. So first off, what is our surface?
Sphere.
We have a sphere. So we're looking at this piece of a sphere in the first octant. Now remember, this is where we have to be careful. We have our surface given to us by this equation. What people are tempted to do is say that capital G equals x squared plus y squared plus z squared minus 36. We don't want to do that. Remember, in our development, we said we needed our G in the form z minus g of xy. So we need to express this in terms of z.
But then how come in the first one we could do it?
Because we had, in our first one, we had z wasn't squared. So we could write z equals 6 minus 2x minus 3y. So then the small g would be 6 minus 2x minus 3y. So in this case, we have z squared. So that's what's changed in this one. So here we would say z equals the square root of 36 minus x squared minus y squared. And the reason this is important is the reason we could express our integral as f dot del g is because when we expressed g this way, the magnitudes of del g canceled. If we don't express del g this way, and the magnitude of del g came from our expression for ds. If we don't express g this way, ds and the magnitude of del g would be different. If we use this for our g, our magnitude of del g wouldn't cancel with the del g that came from our ds. So that would complicate our integral. So for an example like this, you need to make sure you do this. Okay? So that's what I wanted to get through with that example. All right, quickly. We want to find the flux over a closed surface. If we have to find the flux over a closed surface, you have to make sure you take into account all the surfaces. So let's say our field is x plus yi plus yj plus zk. And our surface is given to us by z equals 1 minus x squared minus y squared. And we're bounded at the bottom by z equals 0. So we have a closed surface. You'll see this, sometimes you'll see this written just like we did, I talked about for our line integral. You'll see this written like this. So this little circle means we have a closed surface. All right, so here I'm going to draw a quick sketch of this surface. What does z equals 1 minus x squared minus y squared give us? Paraboloid. Very nice. So we get something like this. And in the xy plane we have a circle. So our boundaries above are this paraboloid. And at the bottom we're bounded by the xy plane, z equals 0. So when we do this surface integral over the closed surface, we have to find the flux through this upper surface and the flux through the lower surface. So we're finding what's flowing out of the entire thing. On the bottom, our unit normal vector, and we're not worried about upward because we don't have just a surface, we have a closed surface. We're just worried about the outward direction. So on the bottom, on the xy plane, what is going to be our normal vector on the xy plane for something flowing out the bottom? Negative k. Our unit normal vector is negative k. And f dot n, f dot our normal vector, is just z. But on the xy plane, what is z? 0. On the xy plane, we're talking about this surface, so on the bottom, z equals 0. So we're integrating 0. So there's no flux out of the bottom of this, on the bottom of this surface. Because f has no z component on the xy plane. All right, on the upper portion, I think we're just going to have time to get this one set up. On the upper portion, G is, our capital G is z plus x squared plus y squared minus 1. Del G is 2xi plus 2ij plus k. F dot del G gives us, when we do our dot product, I'm going to multiply and simplify all at once. X squared plus 2xy plus y squared plus 1. So we're integrating this over the region, this circle in the xy plane. So we're going to use polar coordinates. So we need to convert all of this to polar coordinates, substitute for x and y, and we're integrating from r equals 0 to 1. This is a circle with radius 1. And theta equals 0 to 2 pi. The integrals turn out not difficult to evaluate. So we use polar coordinates, substitute, and our integrals end up not difficult to evaluate. Okay. Let me write, and I'll write it what I ended up with. We get 0 to 2 pi. No, it's a whole thing. 0 to 2 pi, 0 to 1, and I ended up with r squared plus 2r squared sine theta cosine theta plus plus 1, yes. RD theta. All right, homework. Can't forget about that. All right, there you go.